Properties of direction ratios. Welcome back, everyone. Before we dive into today's new topic, let's take a moment to recap what we've already covered. In our previous lessons, we established a fundamental connection: that direction ratios, or doctors, are simply numbers that are proportional to the direction cosines, which we call DCs, of a line. Now, there is a very important distinction you need to keep in mind. While the direction cosines are unique, meaning there is only one specific set of them for a specific directed line, the direction ratios are not unique. This means we can have different sets of numbers that all point in the same direction. In this subsection, we are going to explore the specific properties of these ratios. We'll look at how they behave, why they aren't unique, and how we can manipulate them while still describing the exact same line. Let's get started. Understanding the non-uniqueness of direction ratios. Now that we've established that direction ratios are proportional to direction cosines, let's dive into the most critical property you need to remember. Direction ratios are not unique. What does this mean in practice? It means that if you pick a single, specific line in three-dimensional space, you aren't stuck with just one set of numbers to describe it. In fact, there are infinitely many different sets of direction ratios that can represent that exact same orientation. To understand why this happens, let's look at the underlying math. Remember from our previous discussion that direction ratios, which we can call a, b, and c, are derived from the direction cosines, which we call L, M, and N specifically. We can say that A equals lambda times L, B equals lambda times M, and C equals lambda times N. In this equation, lambda represents any non-zero real number. Because lambda can be any value you choose, whether it's 2, 10, or even a fraction, we can generate an infinite number of different sets for a, b, and c, all while using the exact same set of direction cosines. As we will see in the next slide, this leads to the concept of proportionality, which is the key to identifying when two different-looking sets of numbers actually belong to the same line. The proportionality property. Now that we've established that direction ratios aren't unique, let's look at the specific rule that governs them. This is what we call the proportionality property. Essentially, if you have one set of numbers, let's call them a, b, and c, that represent the direction ratios of a line, any other set of numbers. We'll call them a prime, b prime, and c prime. Will represent that exact same line if, and only if, they are proportional to the first set. To make this more concrete, we use what I call the scalar multiple rule. This rule states that if a, b, and c is your original set of direction ratios, you can pick any non-zero real number, which we'll call k, and multiply your entire set by it. The new set, which would be k times a, k times b, and k times c, is also a perfectly valid set of direction ratios for that same line. If we were to write this out mathematically, it means that the ratio of a prime to a equals the ratio of b prime to b, which equals the ratio of c prime to c, and all of these are equal to our constant, k. As we will see in the next slide, this is very much like following a path where you can increase the distance traveled without ever changing the actual direction you are heading. Real-world analogy, the concept of a path. Now, I know that the idea of non-uniqueness might sound a bit abstract, so let's step away from the formulas for a moment and use a real-world analogy to make this concept more concrete. Imagine you are giving someone directions to walk along a straight path. You could tell them to move 2 meters east, 1 meter north, and 3 meters up. Alternatively, you could give them a different set of instructions. Move 4 meters east, 2 meters north, and 6 meters up. If you look closely at these two sets of instructions, you'll notice that in both cases, even though the total distance traveled is different, the actual direction of the movement remains exactly the same. If you look at the math behind this, the second set of instructions is simply the first set multiplied by a factor of 2. This is exactly how direction ratios behave in three-dimensional geometry. They act just like these instructions. They tell us the slope or the orientation of the line in space, regardless of the magnitude or the length of the vector we are using. This leads us perfectly into our next slide, where we will see this principle applied to a specific numerical example. Illustrative example. Now that we've understood the theory behind how direction ratios work, let's move on to an illustrative example to see this property in action. Let's start with a concrete starting point. Suppose we have a line defined by the direction ratios 2, -1, and 3. Our goal here is to demonstrate how we can generate different sets of direction ratios that all describe this exact same line. First, let's try multiplying our original set by a positive constant. If we choose k equals 2, we simply multiply each component of our original set by 2. This gives us 2 times 2, -1 times 2, and 3 times \text $2, which results in a new set of direction ratios, 4, -2, and 6. Notice how the numbers have grown, but the orientation remains unchanged. Next, let's see what happens when we use a negative constant. Let's pick k equals -1. When we multiply our original set, 2, -1, and 3, by -1, we get -2, 1, and -3. As we'll discuss later in our common mistakes slide, even though the signs have flipped, we are still describing the same line. Finally, let's try multiplying by a fraction to see if we can scale the numbers down. Let's set k to 0.5. Multiplying 2, -1, and 3 by 0.5 gives us 1, -0.5, and 1.5. To conclude this example, look at all the sets we've generated. The original 2, -1, and 3, our first set of 4, -2, and 6, our second set of -2, 1, and -3, and our final set of 1, -0.5, and 1.5. Because every single one of these sets is proportional to the others, they all represent the same line. This perfectly illustrates the non-uniqueness property we discussed earlier. Key takeaways. First, remember that we are dealing with infinite sets. Unlike direction cosines, which are unique for a specific directed line, a single line in three-dimensional space actually has infinitely many sets of direction ratios. Second, we have the principle of proportionality. This is the core of what we discussed earlier. Any two sets of direction ratios that represent the same line must be proportional to one another. Third, this leads us to the rule of scalar multiplication. If you have a set of direction ratios, let's call them a b and c, then you can multiply each of them by any non-zero constant, which we'll call k, to get a new set. K times a, k times b, and k times c as long as k is not 0. This new set is still a valid representation of that same line. Finally, it is crucial to distinguish between direction and magnitude. Always remember that direction ratios are designed to define the orientation or the slope of the line in space. They are not concerned with the length or the magnitude of a specific segment. All right, let's bring everything together. We have covered a lot of ground today, from the definition of direction ratios to how they relate to direction cosines, so let's summarize the key takeaways from this lesson. Now, before we wrap up, I want to point out a few common pitfalls that students often encounter, so please pay close attention to the next slide. Common mistakes to avoid. First, let's talk about the zero constant. Throughout our discussion on proportionality, we used a constant, which we called k. It is very easy to assume that k can be any number at all, but please remember, k cannot be 0. Think about it. If you multiply your direction ratios by 0, your entire set becomes 0, 0, 0. A set of zeros doesn't point anywhere. It doesn't define a direction in space, so it's mathematically invalid for representing a line. Second, be careful not to confuse direction ratios with direction cosines. This is a very frequent mistake. As we established in our very first slide, direction cosines are unique and must satisfy a very specific rule. L squared plus m squared plus n squared must equal 1. While you can multiply direction ratios by any non-zero constant, k, and still have valid direction ratios, you cannot do that with direction cosines. If you multiply direction cosines by a constant, they lose that essential property of summing to 1, and they effectively transform into direction ratios. Finally, keep in mind the concept of sign reversal. If you multiply all your direction ratios by -1, you are essentially flipping the signs of every component. While this still represents the exact same line in space, it's important to remember that you are now representing the line in the opposite direction. Now, before we wrap up today's lesson, I want to touch upon some common pitfalls. As we've seen throughout this presentation, while the flexibility of direction ratios is a powerful tool, it can also lead to a few conceptual errors. Let's look at 3 specific mistakes you should avoid in your exams. If you can keep these 3 points in mind, you'll have a much stronger grasp of how these ratios behave in 3-dimensional geometry.